So, next is heterojunction bipolar transistor HBT. So, in this case what we do, let us first discuss about the limitation of BJT, high frequency limitation. So, already we have seen that for high frequency operation we have to decrease base width, so that transit time decreases. Now, if we decrease base width, then base resistance increases. So, how to then compensate this problem? We can increase doping inside base, but if we increase doping, then reverse saturation current will increase, because from p type base we have holes which drifts into emitter. Now, can we design a BJT which will provide different band gap values to electrons and holes? For example, for a NPN transistor emitter, it emits electron, and it's due to drift motion it will inject electron into base. Now, let us say the band gap for this electron it remains unchanged, but the gap it increases for the holes. So, in that case now the number of holes which will drift into emitter from base, that will decrease, but it will not affect the normal operation of electrons. So, that is how we get HBT. So, why the name heterojunction? Because for this type of device we have to use two different types of semiconductor materials having different band gaps for the emitter and base to obtain this type of property. So, let us see here. Then in general differing semiconductor materials, but obviously they should have similar lattice constant, otherwise they will not match to each other and it will be associated with some impedance. So, for the emitter base and base collector junction, creating a heterojunction. Then injection of holes from base into the emitter region is limited. So, potential barrier in the valence band is higher than in the conduction band. This allows a high doping density in the base, reducing the base resistance while maintaining gain, and typically it can be used at very high frequencies, even a few 100 gigahertz. You can see the band diagram. Left hand side it shows for a PNP type transistor, and right hand side it shows for a germanium based NPN type transistor. So, for this NPN transistor, so emitter, it is emitter and collector both are based on germanium, but the middle base layer it is p type gallium arsenide, two different types of semiconductor. Now, at room temperature the Fermi levels it will align itself throughout the structure. So, accordingly we can draw then the band diagram. So, for N type germanium, conduction band is close to Fermi level, and for p type gallium arsenide valence band is close to Fermi level. Now, if I go back to basic BJT operation of one NPN transistor, you see emitters it injects electrons, and from base we have a problem due to the holes. Now, if I look at the band diagram, electrons which are in the conduction band that actually contribute to conduction current, and the holes in the valence band that will contribute to current. So, holes from the base region it has to traverse to the p side to n side emitter region, and the band the gap in potential, we have a potential barrier here, it is shown by the difference of this valence band, and similarly for the electrons left hand side to right hand side it has to overcome this potential barrier. Now, the potential barrier height it becomes different for electrons and for holes. For this particular example, this potential barrier is smaller under forward biased condition for electrons and it is higher for the holes. So, under a given forward bias condition, then electrons it can easily move from emitter to base, but holes they have a problem here. So, base to emitter movement it becomes restricted. That is how we can decrease reverse saturation current due to this hole movement from base to emitter. So, that is how one HBT it operates, and typical materials used for HBT: silicon, gallium arsenide, indium phosphide, aluminum gallium arsenide, and different types of wide band gap semiconductors like gallium nitride, indium gallium nitride. So, they are being used for designing and fabricating HBT. Here is one example of graded structure based on aluminum gallium arsenide HBT. The junction current it can be given by A into E dn PPO into this exponential function divided by ln, where A this is the device cross section, E is the electronic charge, Vt this is the thermal voltage, it depends on room temperature as well as electronic charge, dn this is the electron diffusion constant, PPO this is equilibrium electron density in the base, and ln this is hole diffusion length. So, current it increases with the device cross section and decreasing hole diffusion length. Now, substrate comparison for different types of active devices. So, you see current density it is a function of base emitter voltage. Here we are showing different types of HBT based in indium phosphide on silicon and gallium arsenide. So, current density it rapidly increases with the increasing base emitter voltage, and for gallium arsenide based HBT you see we need more base emitter voltage compared to let us say silicon device. Next one is a comparison of breakdown voltage for different substrate versus collector doping concentration. So, silicon it has the lowest breakdown voltage, whereas indium phosphide it has the highest breakdown voltage. Now, the electron velocity versus electric field. So, you can see here as I discussed before that electron velocity it is a function of applied electric field. For silicon or indium phosphide, if we keep on increasing electric field, initially electron velocity increases, but at some point it reaches its maximum value. We call that the saturation electron velocity. But for some group 3, group 5 materials like gallium arsenide, gallium, indium arsenide, we see that with the applied electric field initially electron velocity increases, it reaches a maximum value, after that it decreases. So, electron velocity decreases after reaching Vs. So, that means the overall current it also will decrease. So, with increasing voltage current decreases, that means we can obtain negative resistance. We will see later the applications of this type of devices in transferred electron device. Next is thermal conductivity. Thermal conductivity is important because it shows how fast we can remove the generated heat from the device. So, thermal conductivity it depends not only on substrate, but also a function of temperature. You see with increasing temperature thermal conductivity it decreases, and silicon it has highest thermal conductivity among these three, and gallium arsenide thermal conductivity is lower. Next device, Schottky diode. Although we are calling it a diode, but it does not involve any p-n junction. This is basically a metal semiconductor junction, and the metal with semiconductor usually it can be p type or n type, but most popular is n type. Typically doping concentration is higher, so we called it a metal n plus junction. Since we are not using any p-n junction, it is not associated with any space charge region. Then the advantage is that we can avoid junction capacitance, which is usually seen for a given p-n junction. So, what is the advantage of that? We can go for very high frequency operation. So, reverse recovery time, that is very less for Schottky diode. So, some basic characteristics then we can see here. This is a hot carrier diode. So, metal semiconductor junction, typically n type semiconductors are used, and if you look at the current voltage plot characteristics, DC characteristics. So, for p-n diode, p-n junction based diode, in forward biased condition, current increases exponentially after a cut in voltage V gamma, and reverse saturation current usually very small, but if we keep on increasing the reverse voltage, after some point where we have the breakdown voltage, current increases rapidly, but till that point we can represent one reverse biased p-n junction by very high resistance. But for Schottky diode, in forward biased condition almost similar to p-n junction, the current increases very rapidly, but in reverse biased condition we have very high saturation current component. That means it will not behave like a reverse biased p-n junction, or the equivalent resistance in reverse biased condition is much smaller compared to a conventional reverse biased p-n junction diode. Not only that, we see that the cut in voltage for Schottky diode in forward biased condition, it is much smaller compared to V gamma of p-n diode. Similarly, in reverse biased condition, breakdown voltage also much smaller compared to a conventional p-n junction diode. So, this breakdown voltage in reverse biased condition, it depends on the type of semiconductor material we are using, and it is also related to the cut in voltage of this Schottky diode in forward bias condition. So, Schottky diode with lower cut in voltage, it will have higher reverse saturation current also. So, that is why instead of using just 0.1 or 0.2 volt forward voltage drop, in typically 0.3, 0.4 volt are preferred, then in that case to some extent we can decrease the reverse saturation current and increase the reverse breakdown voltage. So, why it is so popular at millimeter wave frequency? Because of very low reverse recovery time. Since it does not have any space charge region, so nothing to so there is nothing to recover from. So, that is why the recovery it's almost instantaneous. Schottky diode does not have any recovery time theoretically, but due to the packaging effect and sometimes modification of the device which are used to decrease the reverse saturation current or to increase the reverse breakdown voltage, it is associated with some capacitance. Usually it is very small, typically less than 1 picofarad. So, that is why the switching time of the order of 100 picosecond, you can compare with the typical switching time for a PN junction diode which is 100 nanosecond. So, switching speed that can be achieved even 50 to 60 gigahertz is possible, and not only that, it has less reverse recovery current and no slow random recombination, because it does not have any space charge region and it is only associated with, let us say, electron flow. So, recombination of holes and electron we can avoid here, and that is why the EMI noise produced by recombination can be avoided. So, it shows the band diagram for a metal semiconductor Schottky diode at room temperature. You see the Fermi levels, it aligns itself throughout the material structure, throughout the structure. Now, for metal, Fermi level it is inside conduction band. So, at room temperature already we have free electrons to move, and inside N type material you see there are just a few electrons at room temperature. Now, under given biasing there will be a thin depletion region, because in N type materials electron density is smaller, in metal we already have free electrons. So, without biasing there will be a very thin depletion region like thing, and the width of this depletion region it decreases with the increasing doping concentration, but very high doping concentration is avoided, otherwise that semiconductor materials it will behave like a metal, and instead of semiconductor metal junction it will behave like a metal metal junction. Now, because of this high doping concentration, the thickness of the so called depletion region is very narrow, and there will be tunneling effect through the depletion region. So, details operation and band diagram we are skipping here in this lecture. Due to this thin depletion, we have one more problem. The problem is that the electric field due to the applied voltage, it mainly appears across the depletion region, and the low reverse voltage rating it is associated, that is why it is associated with very low reverse voltage rating, typically less than 50 volt, and also it has high reverse leakage current. Reverse leakage current it increases with temperature, that is one more problem, and due to that we have instability because of temperature variation. Some recent developments, devices based in silicon carbide, it provides low leakage current and high voltage rating, typically of the order of 1700 volt. In forward bias condition, when we use this Schottky diode as a switch, in forward bias condition it will provide very low resistance, and in reverse bias condition it will provide high resistance, and the metal we consider it as anode, and the N type semiconductor we will consider it as cathode. So, this is the equivalent circuit, simplified equivalent circuit of a Schottky diode. Metal semiconductor junction, it is represented by a resistor R j and capacitor C j. So, R j it has different values in reverse and forward bias condition. In forward bias condition typically a few ohm, and in reverse bias condition it is a few kilo ohm, and then we have R s parasitic resistance, and due to packaging and the external leads we also have parasitic capacitance C p and parasitic inductance L p. So, when we use as a discrete device, sometimes this L p value is so high, it can be even 1 nanohenry, it can limit high frequency operation. So, we have to be very careful when choosing a Schottky diode for any given applications. Next is PIN diode. So, as this diagram shows, it is a P plus I N plus structure. So, I, it represents intrinsic layer. Usually its resistance is very high, since we are not using any doping. Now, since we have P plus and N plus, so the depletion region, it extends deep inside intrinsic region, whereas inside the P plus region or N plus region, the thickness of depletion region is very narrow. So, what happens at lower frequencies, it obeys standard diode equations, but if we keep on increasing the frequency, in that case the diode never turns off, because the reverse recovery time is very high. So, at very high frequency we can use it as a resistor, and the resistance, it becomes a function of the biasing current. So, we can control the resistance by controlling the biasing current, or we can use the PIN diode as a variable resistor at higher frequency. Another advantage due to the wide intrinsic layer is that, since P plus and N plus region and their corresponding depletion layer, they are the separation is large, it is associated with very low capacitance. So, it is inferior as a rectifier, but it makes suitable for attenuators, fast switches, photo detectors and high voltage power electronics applications. So, it shows this with the VI characteristics of a PIN diode in forward biased condition. So, this is the DC characteristics, not the high frequency characteristics. So, in forward biased condition, it obeys diode relationships, also in reverse biased condition, but if we keep on increasing frequency, working principle it becomes different, and in that case it does not obey this diode relationship. Now, in on condition, when we are going to use it as a switch at lower frequencies, then in on condition it can be represented by a resistor, and in off condition, that means in reverse biased condition, it can be represented by a capacitor, and R on roughly it can be given by T I square divided by mu n plus mu p into q. So, T I, this is the thickness of this intrinsic layer, and mu n mu p, they are the electron and hole mobilities. Q is the stored charge inside intrinsic layer, and it can be given by I p n multiplied by tau c. Tau c is the carrier lifetime inside intrinsic region, and in the off state, the capacitance C off, it is equal to epsilon naught epsilon I into A by T I farad. A is the cross sectional area of the device, T I again thickness of the intrinsic layer, and when we apply in switching applications, we will see later that we can define figure of merit of any switch by R into C, because in forward bias or in on state it will give some resistance, in off state it will give some capacitance, and this resistance it and the capacitance, it determines the insulation, the insertion loss and isolation due to switch. So, we have to decrease insertion loss and we have to increase isolation, and we use a parameter, we call it figure of merit for switches. It is given by R on into C O F. We can calculate it theoretically roughly from this given dimensions. This example shows a pin diode when being used as a switch. You can identify the pin diode, and with this diode we have some additional components like resistors and capacitors. So, why they are used? So, let us say we want to transmit one microwave or millimeter wave signal from left hand side to right hand side, and this is the microstrip line, and this pin diode, it is being used in shunt configuration. So, when this pin diode is switched on, that means when it is in forward biased condition, in that case we can replace it by a small value of resistance, typically a few ohm. So, that means the microstrip line, it will be grounded, and there won't be any signal passing from left hand side to right hand side. Similarly, in off condition, this pin diode we can replace by a very small value of capacitor. So, due to this capacitor, almost we can consider as if this path is broken, and there will be power transmission from left hand side to right hand side. So, in off condition, then we have good isolation because of this pin diode, and in on condition this RF signal, it will pass to ground. Now, we have to provide this bias current to keep the diode in forward bias condition and reverse bias condition. That we can do by using DC or RF source that is being connected by this bias connection. So, this bias connection, it will provide the forward bias and reverse bias condition of the pin diode. Now, if we directly connect a DC source here to microstrip line, then whatever RF signal is coming from left hand side, it will also go to this bias connection. So, we have to then somehow stop this RF signal to go to this biasing circuit. So, we can use some inductor here, or we call it bias choke, that will provide very high resistance to RF signal and very low resistance to this biasing. Similarly, we have to somehow isolate this DC biasing source from RF input source or the RF load at the right hand side. So, that is why we are using some blocking DC blocking capacitor C. So, typically C value should be as high as possible, so that it offers very small resistance, or we can replace capacitor simply by short circuit for this millimeter wave signal, but we have to replace the capacitor by open circuit for this biasing connection. In addition to this, we have open stub for matching purpose, and typically sometimes we used a very small value of inductor that can improve the isolation condition. We will see later when we will discuss electronic switches. So, in general, then under 0 or reverse bias condition, it will provide low capacitance, and at very high frequency it will provide high resistance. Typical value at low forward bias current, let us say 1 milliampere, resistance is 1 ohm, switching speed typically 1 microsecond, and figure of merit can be reduced to even 30 femtosecond by using compound semiconductors. So, pin switch performance comparisons in different technology. We have some available switches from markets, and here we are comparing the figure of merit values. We have indium gallium arsenide or indium phosphide based devices, silicon based device, and gallium arsenide based device. So, if we look at the figure of merits, you see indium phosphide or indium gallium arsenide, it will provide 31 point, typical value is 31.2, and it is, or 30, it is having the smallest among all these. For gallium arsenide based device, it is higher. So, smaller is better. If figure of merit is smaller, in that case we can achieve lower insertion loss and high isolation values. So, we will take a break, then we will start transfer electron devices.